So first and foremost, I have a confession to make. I've been in the oil and gas industry for about 15 years, so I've got a long way to go to get to net zero, especially as I'm trying to get beyond net zero. Emnandi was established about 2 years ago with the objective of adopting innovation in polymer manufacturing and sustainability more broadly. Our vision and our expectation is that plastics can contribute to achieving net zero and sustainability more broadly. So first of all, why plastics? Why bioplastics? So plastics contribute about 3.5% of the global greenhouse gas emissions. That's about 2 gigatons per year, or certainly 2 gigatons today. And the vast majority of that is driven by their production. And as much as we're looking to reduce, recycle, that is expected to grow quite considerably and in fact double by the time we get to 2060. So as we're in London, we need to have a London bus and we need to have a London bus calculation. I've picked the number 9. I've spent a lot of time on the number 9, and some of you may have used this to get here today. It takes you to High Street Ken. So we know London buses are pretty efficient when it comes to CO2, but would anyone like to guess how much that 2 gigatons equates to in terms of the London bus CO2 emissions? Any guesses? It's actually 400 million London buses. So the moral of the story is take the tube, right? Okay, let's get back to plastics here. I'm sure you've seen and used quite a lot of them before, and this won't come as a surprise. But what may come as a surprise is how much CO2 is emitted as these plastics are produced. So if we look at some of the most common ones, say polystyrene. Polystyrene is used in yogurt cups, for example. And for every kilo of polystyrene produced, 2 kilos of CO2 is emitted. So that's double its weight. And that's true for the vast majority of conventional plastics that you would use. Bioplastics are a little bit different because, of course, they start from a renewable resource. And the example we have here is polylactic acid, or PLA. Bioplastics, of course, start from absorbing CO2 from the atmosphere when the raw material is grown, when it's cultivated. And in the case of PLA, today, only half a kilo of CO2 is produced for every kilo of PLA produced. And by fine-tuning the production process, it could actually become a net absorber, so absorb a ton of CO2 for every ton of plastic that's produced. And that's how we get to beyond net zero. But that's only half the story, because the other piece is, of course, what happens to plastics. So the rates of recycling are increasing considerably. Nonetheless, only about 17% of plastics are expected to be recycled by 2060. The vast majority of them will still be either incinerated, mismanaged, but worst of all, a huge proportion of plastic will still end up in landfill. And that's the piece that we are trying to address, because bioplastics come in 2 forms. They are bio-based, but they are also compostable. And we're looking at plastics that actually meet those 2, that are both bio-based and compostable. So how do we do that? And what do we do at Emnandi Bioplastics? Well, when we first started, we thought it'd be really easy. You just produce plastic, bioplastic, and everyone understands the problem, and it'll just be consumed. But it isn't that simple, because there are quite a number of challenges, from cost, from their properties not being quite right. And we get into that, the whole life cycle, if you will, from the production of the bioplastic itself, from developing specific blends and optimizing those blends, to helping converters, to helping producers of products integrate them into their production lines. And finally, to also think about how they are designed, and in particular, how can we make them easier to recycle? How can we make them more compostable, easier to compost? And that's sort of a change in mindset to how conventional plastics are designed today. But the project I'd like to take you through for the second half of this talk is around the manufacturing. So one of the projects that we're involved in manufacturing. And the material that this involves is called polybutylene succinate. And I challenge you to say that after a few drinks at the networking session. So we'll just call it PBS for short. What you see on the right are examples of PBS products. They've been compounded, so formulated in a very special way so that they can actually produce, you can produce a cup that you can drink coffee from, so it is heat resistant. But PBS is exceptionally versatile because it can also be used for packaging, and it is home compostable, so it'll compost in your normal home composting facilities. It's produced from a renewable resource, so we are looking to produce it from molasses in particular. It goes through a series of chemical transformations, so a fermentation process and then some transformations. And then finally a resin is produced, which is compounded. Now what's fascinating, I think, about bioplastics is that you can also mechanically recycle them, and you can chemically recycle them fairly easily and take them back to their original starting points. So our concept is a very compact PBS production system. It's a 10,000-ton integrated system that does everything in one unit, if you like, that can be bolted on to a sugar mill or any facility, perhaps some for forestry industry, where they have perhaps a waste stream that is rich in sugars that can be, in the first instance, fermented and purified. So at the end of this fermentation process, you have an acid called succinic acid. That's where the S comes from. That is then hydrogenated. In other words, hydrogen is added to then produce an alcohol. The acid and the alcohol are polymerized. And then finally, very unique to a plastic production system, it's also compounded to give you a material similar to the one that you saw, so that compounding does not have to happen afterwards. And then finally, it's obviously stored. So the key features of this is that, first and foremost, it's derived from something that is not in competition with the food source. We're looking to localize the supply chain. That's why we make it nice and small and compact, so you're not having to bring your raw materials from all over the world. It's fully integrated and plug and play. So obviously we've not done this alone. This is the product of about 18 months of work across 18 partners, mostly based in Germany. And these partners are across the value chain, because this is the only way you can make these projects a success. So everything from biotechnology, the monomer and synthesis, the polymer synthesis, the compounding, processing, and very importantly, recycling as well. And that's why you see, obviously, Veolia up on that list also. So where are we? Where do we go from here? So we've established the pilot plant. So all of the processes have been developed at a pilot scale. And our next stage over the next 24 months is to undertake a basic engineering design, followed by the first demo unit, and the last step is, of course, to scale it up and take it across Europe and beyond Germany. If you would like to get involved or find out more, we do have a forum that we're hosting in Germany in a few weeks, and if you would like to find out more, please scan that or get in touch. That's all I have. Thank you.
Thank you. Thank you, Anita. That was, yeah, super on time. Does anyone have a question? Great.
Hello, thank you very much for your presentation. I understand how it works in terms of, like, it was very clear, but I don't understand how it removes CO2 when you say it goes beyond, if you can explain. Thank you.
Absolutely. So basically, if you take sugarcane, for example, which is the source of that material, when any tree or plant grows, it absorbs CO2. And that's where you start your carbon accounting. By contrast, when you mine oil or the crude oil, a lot of energy is consumed and that produces CO2. So that's the main difference there.
Hi there, I've just got a quick question. You commented that the material was heat resistant.
Yep.
And I just wonder if you could elaborate a little bit further. Particularly, what range of temperatures can it handle?
That particular one, you could pour boiling water into it and it will withhold it. So it's about 90, 100 degrees. That's the temperature range.
Any other questions? Another, of course.
Thank you. When you say it's plug and play,
Yeah.
does it mean that like it's a transportable technology that one can use like at home?
At home. That's a good. Well, maybe not at home, but so imagine a container. The entire unit would be held within a 40-foot container. It would all be built at the engineering site, transported, and then plugged in to a refinery, for example.
I'd like to riff off that. I work for Clean Tech Group. We are a consultancy that we pair up technologies with large companies and to pilot them. So we work with a lot of drinks companies, and looking at your solution seems perfect fit for a Coca-Cola or a Pepsi. Is that the type of company you've identified to be perfect customers? If not, who are your perfect customers?
Great question. At the moment, we're looking at starch producers, sugar producers, perhaps pulps, mills, who may have side streams of C5 sugars that can be used for this. So it's more agri-tech companies at the moment. But I'd love to explore that, actually.
Yeah. Great, great. Any more audience questions?
Okay, it all sounds great in theory. What about the waste management infrastructure? The infrastructure that we have at the moment can't deal with biopolymers.
That's why you're absolutely, well, first of all, that's why we're staying away from recycling. So we're not competing with anything that can be recycled. And secondly, the infrastructure that we have today can handle industrial composting, which is what those polymers would undertake. What's more, they can also be home composted, and that's what we're striving towards. But that is a very good point and something we have to work at.
Yeah, building on that again. What are, I guess, the end-of-life risks for this product? Where would it be dangerous or disruptive in the circular economy for it to end up?
So it doesn't address the issue of plastics ending up in the ocean, right? So it won't necessarily degrade in the ocean. But it will degrade under industrial composting conditions, so it does still require the responsibility of people to dispose of it correctly. But at least there is an alternative solution to landfill, especially. So what we do is we target things that cannot be easily recycled. For example, a toothbrush. It can't be recycled, it will end up in landfill. This gives you an alternative solution.
Just on that point on landfill, is there a chance a typical polymer in landfill would be inert? Is there a chance that it could break down to either CO2 or methane at end of life in the wrong place?
Sorry, I couldn't hear you very well.
Sorry, in a landfill, is there a chance that it would break down to something like CO2 or methane?
That's correct, which is why we would advocate that it is dealt with correctly, not a landfill. Yeah.
I'm going to take some more time. I think maybe the last slide showed this wonderful, consortium and partnerships and of loads of different players that are critical to bring in anything good in circular economy. So what would be your advice to other innovators trying to launch a product in this industry and wanting to create as good as partnerships as you've done?
I think the first thing is you have to have a vision. So with us, we knew Germany was an ideal place because there's a lot of sugar and they consume a lot of plastic, and that's how we started. And actually initially we wanted to get into PLA, not PBS. But then as we explored the German market, we came across this, and we were flexible to then change direction and bring all of the skills that we have into this project. So I would say it's about having vision, exploring, and being flexible.
Great, thank you. And we're perfectly on time, so thank you.
Thank you very much.